Welcome back.
So now let us look at the operation during positive half cycle. Sorry, negative half cycle. So during negative half cycle, put the polarity for negative half cycle. Okay. This is the anode terminal and this is the cathode terminal. So in the negative half cycle, as you can clearly observe that both Vs and Vk are trying to circulate the current in the anti-clockwise direction or in the designated path. So both Vs and Vk help each other in reverse biasing the diode. So you can write both Vs and Vk are reverse biasing the diode. So we have already seen in case A, so I can write this is equivalent to case A. So in case A, that is when Vs was less than Vk, the diode was reverse biased, and during reverse biasing operation the voltage we found 0, right? So V0 can be given on the basis of KVL. So you can write something like apply KVL in anti-clockwise direction. So minus to plus Vs minus to plus V0 is equal to 0. So diode is getting reverse biased. So obviously, the diode symbol needs to be replaced with an open circuit equivalent, and current through the circuit becomes 0 amperes, and due to which there won't be any voltage available across Rs. So you can directly write Vs minus plus V0 is equal to 0. That implies V0 is equal to minus Vs. So negative half cycle. So in summary, what we can conclude is that during positive half cycle, for input less than Vk, output is equal to input, and for input greater than Vk, output is equal to Vk. So this is AC and this is DC. And for the negative half cycle, just now we discussed, for the entire negative half cycle, the diode is driven in reverse biasing mode, hence output is equal to negative half cycle of the input. So this is basically AC. Alright, so now let's plot the input and output waveforms. First let us plot the source or input voltage waveform. This is Vm and this is minus Vm. Then let us plot the output voltage. So the source comparison was present for the positive half cycle, right? And the operation of the circuit during positive half cycle was due to the presence of Vk, and Vk is a DC value. So what you have to do is you have to plot a straight line or draw a straight line, something like this, the positive half cycle, and you can name this line as Vk. Okay, so when you draw this Vk in the positive half cycle, so this Vk will create or gives some transition points, right? So draw these transition points onto the output axis as well. So what is the use of these transition points? So these transition points will help you in sketching the waveform. So what you have seen is in the analysis, as long as input is less than the threshold voltage, output is equal to input, right? So for the values of the input less than Vk, output is input. So for the values of the input less than Vk, your output going to be Vs. So I have drawn a sinusoidal output here. And the moment input exceeds Vk value, the moment input exceeds the Vk value, output is equal to Vk. So beyond Vk, there won't be any sinusoidal output, right? So beyond Vk level, the output is held at plus Vk value. And once again, when the input falls below Vk value, the output is equal to EAC. So what you are seeing is that the positive half cycle of the output is getting clipped at Vk level. Okay. And if you look at the negative half cycle, we see that for the entire negative half cycle, output is equal to minus Vs. So just like your ideal clipper, there will be a complete negative half cycle. The maximum value of the negative half cycle of the output is minus Vm. Now let me keep the two waveforms side by side. So this waveform is for ideal diode, and this waveform is for practical diode. So in case of ideal diode, what you are seeing over here is that the positive half cycle of the input is clipped at 0 volt level. On the other hand, if you look at the practical diode, wherein we have considered the barrier potential as Vk, the output, the positive half cycle of the output is not clipped at 0 volt level. Instead, the positive half cycle of the output is clipped at Vk level. So if you consider a silicon diode, then probably you will get the clipping action at 0.7 volts level. And if you consider a germanium diode, then this Vk point going to be at 0.3 volt level. So this is how the the barrier potential affects the waveform shape. And now let's plot the transfer characteristics. Plus Vs, minus Vs, plus V0, minus V. And on the either side of x-axis, mark the maximum values of the input, plus Vm, minus Vm, and also mark the Vk level. So the Vk was affecting the positive half cycle of the input, so let me mark Vk in the positive half cycle. So somewhere here I'll mark Vk, and also along positive output I'll mark Vk. And in the waveform, what we have seen is, as long as the input is less than Vk, the output is equal to input. That means to say EAC. So you can draw a small cube, by taking the help of Vk value plotted along V0 and Vs. Okay, so as long as my input is less than Vk, output is EAC. So straight line. Okay, and for the values of the input greater than Vk, the output stays at plus Vk level. So this is what you get for the positive half cycle. And for the negative half cycle, you don't have to worry, because for the negative half cycle of the input, output is equal to negative half cycle of the input, right? So you mark minus Vm along negative y-axis and make a small cube by taking minus Vm along x-axis and minus Vm along y-axis, and draw a straight line. So basically you have complete AC output for the negative half cycle, and for the positive half cycle you have DC level as well as AC level. So this is your transfer characteristics. I hope that you have understood the operation of positive clipper, positive parallel clipper. So now let us look at negative parallel clipper. Negative parallel clipper. So in case of negative parallel clipper, all what you have to do is you have to just flip the diode orientation. So this is how the circuit looks like. So this is the circuit of a negative parallel clipper. So let me consider the ideal diode analysis. So ideal diode analysis as in Vk is equal to 0 volts. Okay. So first let us analyze the circuit for a set of positive half cycle and then for a set of negative half cycle. So let me write during positive half cycle. So let me redraw the circuit with the polarity for positive half cycle. So as you can clearly observe that for positive half cycle, the negative terminal of the source is getting connected to anode terminal of the diode, and the positive terminal of the source is getting connected to cathode terminal of the diode. So we call this particular connection as reverse biasing connection. So for the entire positive half cycle, diode is kept in reverse bias mode. Hence, diode can be considered as an open circuit element. Okay, so open up the diode terminals and try to apply KVL to obtain the output. So let's do that. Source, limiting resistor. So we'll open the diode terminals. Okay, so this is your equivalent circuit, right? So diode is open circuited, hence current flow in the circuit is 0 amperes. So apply KVL, KVL in clockwise direction. So minus to plus, Vs, voltage across Rs is 0, then plus to minus is minus V0 is equal to 0, or V0 is equal to Vs. What is V0 is equal to Vs? V0 is equal to Vs means output is equal to positive half cycle of the input. So you can simply write positive. So that's the operation during positive half cycle. Next, let us consider during negative half cycle. The polarity of the source needs to be reversed. But the sense in which we measure the output will not change, right? So this is your Vs. So in order to facilitate negative half cycle, let's consider upper side negative and lower side positive. Okay, so this is your cathode and this is your anode. So as you can clearly observe that the anode terminal of the diode is getting connected to positive terminal of the supply. So we call this particular connection as forward bias connection, right? So what you can say is that diode is forward biased, right? So whenever the diode is forward biased, what you can do is you can replace diode with a short circuit equivalent. And let me redraw the circuit. This will just adds more clarity. So short circuit, I'm creating a short circuit across the diode contacts. So it's a closed circuit, so there will be a current flow. And what is that you are observing basically over here? So basically you are observing the output getting measured across the short circuit. Right. So voltage measured across a short circuit element is 0. So V naught is equal to 0 volts. V naught is equal to 0 volts. So as you can clearly observe that for the positive half cycle, V naught is equal to Vs. So that means to say this particular clipper is allowing a positive half cycle to come across the output. On the other hand, it won't allow the negative half cycle to come across the output. So negative half cycle is clipped. Okay. Now let us plot input and output waveforms. So this is your input. And below the input, let's plot the output. Duration of positive half cycle, duration of negative half cycle. So during positive half cycle, output is equal to AC. Output is equal to Vs. Alright. And for the negative half cycle of the input, output stays at 0 volt level. So what you can say is that negative half cycle is clipped. So negative half cycle is clipped, and therefore it is called as a negative clipper. Let's also draw the transfer characteristics. Minus Vs, plus Vs, plus V naught, minus V naught. So for the positive half cycle, maximum limit is plus Vm, and for the negative half cycle, maximum limit is minus Vm, and for the positive half cycle of the input, the output is AC. So you also mark plus Vm along the positive y-axis. So that's your transfer characteristics for positive half cycle. This is AC and 45-degree inclination. Alright, and for the negative half cycle, what are we seeing? We are seeing a 0 volt output, hence you can say that the output simply overlaps the negative x-axis. So this is the transfer character. So you can also try for negative clamper with a practical diode. Okay, it's very simple. So I'll tell you a shortcut here. So what do you mean by a practical diode? A practical diode is a diode which possesses finite barrier potential. Right. So in case of ideal clipper, what happened was the output was getting clipped at 0 volt level. Right. So in case of a practical negative clipper, what happens is that output is not going to get clipped at 0 volt level. Instead, the output is going to get clipped at minus Vk level, right? So let's see how exactly it happens. So negative clamper with a practical diode. So first let us draw the equivalent circuit. So this is your diode. So what I will do, this I will consider it as ideal diode in series with the barrier potential. So this is the anode terminal of the diode. So in order to place the barrier potential, what I have to do is I have to connect the negative terminal of Vk to the anode terminal of the diode. So by doing that, you can say that the barrier potential opposes the diode conduction, and this is your Vk. And this is where you will measure your output. Okay. So the operation is similar to positive half cycle. Basically, it's the complement of the positive clipper. So it's a clipper. Alright, so first let us consider positive half cycle. Since there are two sources, what are the two sources? Vs and Vk. So try identifying pressure getting applied by the sources. Diode, barrier potential. So the output. Right, positive half cycle. So upper side positive, lower side negative. Okay, and you observe carefully here. So with a given polarity, Vs is trying to circulate the current in the clockwise direction. And with respect to the polarity of Vk, we see that Vk is also trying to circulate the current in the clockwise direction. So both Vs and Vk are helping each other in reverse biasing the diode, right? So you can see that positive terminal of Vs is connected to cathode and negative terminal of Vk is connected to anode. So both Vs and Vk are trying to circulate the current in the clockwise direction. By doing so, diode is maintained in reverse bias mode for the entire positive half cycle. And due to which what happens? Due to which the diode can be replaced as an open circuit element. So I is equal to 0 amperes. So when you apply KVL, CWD stands for clockwise direction, minus to plus Vs, voltage across RS is 0, plus to minus is V0. So Vs is equal to V0. So Vs is equal to V0. That means to say output is equal to positive half. And now let us look at the negative half cycle. So during negative half cycle, reverse the polarity for the source and then retain the connection as it is. Okay, so we have placed the polarities for Vs. Right, now you try to identify the pressure. So minus to plus, so the source is trying to circulate the current in anti-clockwise direction. On the other hand, Vk is trying to circulate the current in clockwise direction. Okay, so for the negative half cycle, we see that Vs and Vk are opposing each other. You can write Vs and Vk are opposing each other. There comes the source comparison. So you can write source comparison comes into picture. Okay, so what if the input source Vs is less than Vk? And what if the input source is greater than Vk? So this is what we have to do. What if the input source is less than Vk, and what if the potential of input is greater than Vk? So if the potential of Vs is less than Vk, you can say that Vk is dominating. And if Vk were to dominate, you can see that the negative terminal of Vk is connected to anode terminal of the diode. So whenever Vk is dominating, diode gets reverse biased. Okay, on the other hand, if Vs is greater than Vk, you can say that Vs is dominating. Okay, and if you consider Vs, okay, as the dominating source, you can clearly observe that the negative terminal of Vs is connected to the cathode terminal of the diode. Hence, you can say that the diode is getting forward biased. So when Vs is less than Vk, Vk is dominating, and Vs is greater than Vk, Vs is dominating. Right? So when Vk dominates, diode gets reverse biased. So for case here, let's draw the equivalent circuit. So diode is reverse biased, hence you have to open up the diode terminal. So apply KVL in anti-clockwise direction. ACWD, anti-clockwise direction, minus to plus Vs minus to plus V naught is equal to 0, or V naught is equal to minus Vs. So output is equal to negative half cycle of input. Now let's see what happens when VSC is dominating. So when VS is dominating, as I was mentioning that, the negative terminal of Vs is connected to cathode terminal of the diode. So you can say that diode is forward biased. So when the diode is forward biased, the equivalent circuit looks something like this. So diode is forward biased, hence short circuit across the diode. And this is V naught. Right. So what do we see? So output is getting measured across Vk. And you can clearly observe that the negative terminal of Vk is basically connected to plus V naught, and positive terminal of Vk is basically connected to minus V naught, and therefore output V naught is minus Vk because the polarities are different. Alright, so output is equal to minus Vk, and you can say that this is DC value. So the negative half cycle of the input is getting clipped at minus Vk level for a practical negative clipper. So let's plot the transfer characteristics as well as the input-output waveforms. So your input Vm minus Vm, and this is for your output. Okay, you have to draw the threshold voltage over here. So the threshold voltage was basically influencing the negative half cycle of the input, hence draw Vk in the below the reference axis. So this is your Vk level. So obviously this Vk will create two transition points with the negative half cycle of the input. So draw these transition points. Okay, and from the circuit operation we had seen that for the entire positive half cycle of the input, the output was sinusoidal. So output going to be the replica of the input. Okay, and for the negative half cycle, the source comparison was coming into the picture. So as long as the input is less than Vk, output is equal to input. And the moment the input exceeds Vk value, the output was equal to minus Vk. So basically this type of waveform, you are going to get it. Okay. So you can say that the negative half cycle of the output is getting clipped at minus Vk level. And accordingly you can plot the transfer characteristics as well. Vs minus Vs, V0 minus V0 plus Vm minus Vm, and plus Vm for the output. So for the entire positive half cycle of the input, output is a positive bound signal, hence straight line at an angle 45 degrees. And for the negative half cycle, the threshold voltage was coming into the picture, so mark the levels accordingly and draw a small Q, right? And what you are seeing is that as long as the input is less than Vk, output is equal to input. Okay. And for the values of the input greater than Vk, output is minus Vk. Output is minus Vk. So AC, AC and DC. So that's your negative clipper. Okay. So to summarize, in today's class, what we studied was a positive clipper with ideal and practical diode, and a negative clipper with ideal and practical diode. So in the next class, let us look at something known as a double-ended clipper, in which positive parallel clipper is cascaded to a negative parallel clipper, and by doing so you will be able to shape both the positive half cycle of the output as well as the negative half cycle of the output. Alright, so